Mycelium bricks are made from the root-like fibers of fungi grown on agricultural waste like straw or corn stalks. You mix mushroom spores with this waste, pour it into molds, and let it grow for about 5 days at room temperature. No heat, no heavy energy input, just nature doing its thing. Once dried, the material is lightweight, fire-resistant, water-resistant, and mold-resistant. It's also organic and compostable, which is a big deal for reducing construction waste. Now, revolutionizing is a strong word. These bricks are being used in experimental projects like the 2014 Hi-Fi Tower in Manhattan, where architects built a 40-foot structure from mycelium bricks. They're great for non-load-bearing structures. Think insulation, panels, or furniture, because they're sustainable and low energy to produce, but their compressive strength is a limiting factor. Concrete can handle about 4,000 psi, while mycelium bricks max out at around 30 psi, maybe 0.2 MAP in some tests. That's why they're not replacing structural beams anytime soon. Let's get into the calculation side. Bear with me, I'll keep it conversational but thorough. The revolution hinges on sustainability metrics, embodied energy, carbon footprint, and cost. Here's how mycelium bricks stack up against concrete. First, embodied energy. Concrete production is energy intensive. Think cement kilns burning at 1400 degrees Celsius. Producing 1 cubic meter of concrete releases about 1,800 megajoules of energy and roughly 300 kilograms of CO2. Mycelium bricks? Almost zero energy input beyond harvesting agricultural waste and letting fungi grow. The process uses ambient conditions, so you're looking at maybe 10 to 20 megajoules per cubic meter for handling and drying, max. That's a 99% reduction in energy. Carbon-wise, mycelium bricks sequester CO2 during growth, potentially offsetting 10 to 50 kilograms per cubic meter, depending on the substrate. Now, weight and material efficiency. Mycelium bricks are crazy light, about 43 kilograms per cubic meter versus concrete's 2,400 kilograms. That's 60 times lighter. You could stack mycelium bricks 40 feet high for non-structural uses like walls or insulation. This reduces transport costs and emissions. For a small building, say 100 square meters, you'd need about 10 cubic meters of material for non-load-bearing walls. That's 430 kilograms of mycelium bricks versus 24,000 kilograms of concrete. Transporting concrete might burn 1 to 2 tons of CO2 for that volume, while mycelium's lightweight nature cuts that to under 100 kilograms. Cost is trickier. Mycelium bricks are still experimental, so economies of scale aren't there yet. Producing a cubic meter might cost $50 to $100, factoring in labor, substrate, and minimal processing. Concrete's cheaper, around $20 to $50 per cubic meter, but requires expensive infrastructure like batching plants. If mycelium production scales up, say, to millions of bricks annually, costs could drop to match or beat concrete. But challenges like consistent quality and large-scale fungal cultivation make this a long-term bet. Now, the environmental calculation. Construction accounts for 8 to 10% of global CO2 emissions, mostly from material production. A typical concrete building emits about 1,000 kilograms of CO2 per 100 square meters during construction. Swap in mycelium for non-structural elements, and you could cut that by 20–30%, depending on the design. Plus, mycelium bricks biodegrade at the end of their life, unlike concrete, which sits in landfills. If a building uses 10 cubic meters of mycelium bricks, you're saving maybe 3,000 kilograms of CO2 compared to concrete for those components. Here's a quick numerical comparison for a 100 square meter building. Concrete walls, 10 cubic meters times 2,400 kilograms per meter equals 24,000 kilograms of CO2. Energy, 10 times $100. Cost, $500 at $50 per meter. Mycelium walls, 10 cubic meters times 43 kilograms per meter equals 430 kilograms. CO2 emissions, mycelium bricks, 100 to 100 kilograms sequestered. Energy, 10 times 20 mJ equals 200 mJ. Cost, $1,000 at $100 per meter, pre-scale. The catch? Mycelium's low strength limits it to niche applications for now. Scaling production and improving compressive strength, say by mixing with materials like miscanthus, could change the game. Researchers are also testing mycelium components for insulation, where low thermal conductivity and high acoustic absorption shine, potentially outperforming synthetic foams. It's not a full-on revolution yet, but mycelium bricks could shift construction toward a circular economy. If we crack the strength and scaling issues, we're talking a material that's cheap, green, and grown from waste. That's a pretty cool future to calculate.